Welcome guys to one more lecture about our course Python Programming, a hands-on course for beginners. This is Daniel Pinheiro from danielpm1982.com, and in this lecture we will prepare our environment for creating our very first application of Python. So, some informations I gotta pass you before we start coding. First, regarding the installation of the main apps we're gonna need. For this lecture, you should have already watched the videos about Anaconda and Conda attached to the end of this course. So I've recorded two videos, one about Anaconda as a whole and another one about Conda, and we're gonna use both of them until the rest of the course, so it's essential for you to know them well, especially conda and the basic conda commands that we're gonna use to manage our internal dependencies from our Python projects, as well as to create our virtual environments. So if you haven't seen these videos, go there at the end of the course at the appendices and you find these two videos as bonus lectures or appended lectures. But these two, at least, they're quite important, so you gotta watch them first before we start developing our project. So if you haven't seen them, stop this video, go to the end of the course, look for these two videos, one about Anaconda and the other about Conda. And later, after you watch the videos, you come back to this video and then you can proceed. So after watching those videos, you gotta install Anaconda in your operating system so that we can create our project's environments locally before sending them to remote repositories, specifically to GitHub. And also you gotta have installed locally also the Git application. I've also let a reference at the end of this course telling you how to install that, either you're using Linux as me or if you're using any other operating system as Windows or Mac OS. Why do you have to use Git and GitHub? Basically because it's the standard nowadays to share code on the web, and also because we can easily integrate GitHub with Colab. You see that Colab is the way we will use to run our codes remotely at Google servers, so it's easier to have a GitHub project to simply point that out from Colab in order that Colab fetches that remote repository and anyone with the Colab link can run your code and see it running in real time. So as we're gonna see in our workflow, we're gonna create a Git and GitHub project inside which we're gonna put all our projects there. Inside the local and remote project, we're gonna also create the main Anaconda virtual environments through Conda. And finally, we'll import that project remotely to Colab in order to run it remotely. So we run our projects locally in our machines using Anaconda environments, but we'll also run our projects remotely by using GitHub together with Colab. So all our libs, our dependencies we are about to use, including Python core libs, external libs, and IDEs, will be inbuilt to the virtual environments we'll be creating with Anaconda. So although I've left some videos at the end of the course about standalone installations of VS Code, PyCharm, we are not using these standalone installations. We'll use the inbuilt installations of these IDEs already included at our Anaconda virtual environments. So what we are not going to do during this course. install Python or the Python virtual machine or interpreter, and we definitely won't modify any native installation of Python at our machine. Why? Well, because we won't need any Python installation on our operating system. We're gonna use Anaconda virtual environment, so everything that our environments are gonna need will be installed inside the environment itself. It's a closed or isolated environment that we're gonna use, so no need to install anything in our operating system. Everything that we gotta need, including the IDEs, the Python core, any external libs that we eventually use, will all be installed inside the virtual environments we'll have created by Anaconda and Conda. So even the Python itself, or the Python virtual machine or interpreter, we won't need it installed at the operating system, and we also shouldn't change any native installation of it on our operating system, because some of the apps you have in your operating system, they may depend on that native installation. So if you change, for example, the version that comes with your Ubuntu Linux installation, most of Linux apps that use that version of Python probably won't work anymore. So it's not advised to change your native installation of Python, nor we're gonna need any additional installation on the OS level. We are of course using Python, but inside the virtual environments we're gonna create with Anaconda and Conda, but that will be a version of Python only for that virtual environments and all the projects inside it. The operating system won't even know that we are using that Python internal to our Python projects. So this is the standard and the advised way of working with Python and all Python dependencies, always using isolated environments, similar to what we use, for example, when we Dockerize applications. Actually, one of the ways of deploying Python applications is through Docker images that are instantiated into Docker containers that executes Python and executes any Python script inside that Docker container. But this course is not about Docker, so we'll use a different approach for deploy and run our applications, which, as I've said, is by having the project at GitHub and then importing it to Colab. And at Colab, we'll use one of Google's borrowed servers to execute our Python notebook with all the script code there. But think of it always in a way of isolating all your dependencies inside either a Dockerized container with an isolated environment inside that container, or at least inside a project with its own virtual environments, for example with Anaconda environments, which is what we're gonna use during this whole course. So another reason why we are not installing Python on our operating system, neither change any Python installation at it, is because for having Anaconda and Conda installed at the operating system and run, you won't need any previous Python installation at your operating system. Why? Because Anaconda and Conda already have their own Python inbuilt, independent from the operating system. It's not the Python that we're gonna use inside each of our projects. Each project we create with its own environment will have its own Python version or its Python interpreter or Python virtual machine. But the Anaconda and Conda installations we install at our operating system, they already have their own Python virtual machine or Python interpreter inside the Anaconda installation itself. So both for Anaconda and Conda, as for our individual projects, Python version or the Python virtual machine or interpreter will all be separated from the operating system, and they will not depend that we have Python installed at the operating system level. And lastly, if we really needed to install Python at our operating system, for example, at our Linux Ubuntu, this would demand advanced operating system knowledge. And this course is not about operating systems. It's a little bit tricky to install Python or a second version of Python in a system whose most apps already use the native installation of Python that comes with that system. So we would risk breaking all the apps from our operating system if we wanted to install Python directly on the operating system instead of using Python versions only in each virtual environment of each project we're going to create, isolated inside those virtual environments and not on the operating system. So imagine if we wanted to install different versions of Python directly on our operating system, it would be actually pretty messy. It's always preferable that we work with isolated Python dependencies, including the Python itself, and only inside virtual environments created using Anaconda and Conda. Either if you Dockerize it later for deployment or not. So this is the gold standard that any real professional uses in the industry, so that's what we're gonna use for not messing with our operating system and risk breaking it. And another thing that we are not going to do during this course is to install standalone IDEs as VS Code, PyCharm, Spider, etc. Why? Also because we won't need them as we are using Anaconda and Conda virtual environments, and together with the environments we already have access to any of these IDEs inbuilt to the Anaconda installation, either through its graphical user interface or through the CLI code of Conda. So if we weren't using Anaconda or Conda, then we would need to install these standalone installations. Then we would need to install at least one of these IDEs and have a local installation of Python on our operating system to point out that from the standalone IDE. But again, if we are using Anaconda and Conda, which is always the advisable way to work with Python environments, we not only do not need to have Python installed directly in our operating system, and we can use different versions of Python for each virtual project we create with Conda, but we also do not need to have standalone IDEs at our operating system as well. Why? Because they are already built to Anaconda environment and are accessible through any project we create with Conda. So what we are actually going to do during this course, first we gotta install Git, and remember that Git is a local application that you gotta install in your operating system, while GitHub is a remote application or a web application that help us manage remotely our repositories at remote GitHub servers. So one thing is the Git application that we got installed locally to manage our commits and to do the versioning of our project versions. And another thing is GitHub which is a completely online and remote application that manages these projects when we push the local projects to the remote servers of GitHub. And why don't we use only Git? Because we want to share our application, we want to deploy it or automate the deployment using CI/CD, for example with GitHub Actions, or Dockerize it and publish the Docker image somewhere for others to download and create the containers to instantiate the projects in their local machines, whatever. But if we only use Git, we'll be able to run the application locally in our machine, but we won't be able to share the code remotely. So you gotta use Git for managing the versioning of our applications locally, but we also gotta use GitHub for managing it and sharing it from the remote servers of GitHub. So not only we gotta install Git locally, but we gotta have an account on GitHub for managing those same projects remotely at GitHub servers. So if you haven't installed Git yet, please install it. And you gotta install in your operating system directly. It's not included in Conda or in Anaconda environments. It's a completely independent application. And you also gotta have a GitHub account. So if you haven't done your sign up to GitHub already, also create accounts there, because we're gonna need it to share our code through a GitHub link directly, the source code, as to integrate with Colab and then share a Colab link with the code running for others to test it and see it at runtime. So also, if you haven't installed Anaconda locally yet, please install it. We're gonna need it to create our virtual environments and manage all dependencies inside our project. And a last thing, if you haven't any Google accounts, please create one. Why? Because we're gonna need it for accessing Colab in order to integrate our Colab file with the GitHub profile and import our project to Colab and then test it running remotely at Google servers, as well as share the Colab link for others to have our projects running at Colab. At GitHub, you only share the source code of your application. At Colab, you share not only the source code, but the source code at runtime. So you see that at Colab, when we share the link of Colab, we not only have the source code of the project we've written, but we also have the outputs of these projects, similar to a web application, an HTML execution, as we're gonna see when we start using jupyterlab or jupyternotebook. We have the source code and we have the source code outputs or the source code actually running. While at GitHub, we only have the source code. And all of this will be completely free. There are actually other ways that you could deploy the applications at, for example, AWS or GitHub Actions in any CI/CD, continuous integration, continuous deployment. But these other ways wouldn't be free, so I chose to show you this completely free workflow, which is pretty professional while being also completely free. So don't worry that you won't have to pay anything for following this specific development workflow we're gonna use. So this is the development workflow we're gonna use throughout our course and for all projects that we're gonna create in each of our practical lectures, from the first until the last subject we're gonna tackle. So the first activity of our workflow is to create a course repository and clone it to our local Python workspace. So we could create remote GitHub project for each project we create at each of our lectures, but instead of doing so, which is the standard in the industry, for every project you create locally, you also create a single and independent project at GitHub. But in our case, just as a matter of didactics and organization, as we're gonna create many small projects using one same anaconda environment, we can exceptionally put all our projects inside one base GitHub and Git project, so that all those projects will use the same base anaconda environments. So we'll have a base GitHub and Git project, and we'll put all our projects for every class inside that base project, since the first project until the last one of this course. So we have only one GitHub project created, and inside it we'll put all the individual projects of our lectures inside it. Then after we create the GitHub project remotely and clone it to our local machine, we then use anaconda and conda to create a virtual environment inside that one and only Git project folder, so that any individual project put inside will use that same virtual environment, which will be managed at the base project. So all the projects we're gonna put in the base course folder will have access to that anaconda virtual environment inside that workspace we're gonna configure. And we'll create that virtual environment only once, but we can of course change with conda the dependencies of it later, for example adding any additional package or managing the dependencies in any other way we need. So after we create the GitHub project remotely and clone it locally, and after we create the virtual environment, we then will call or initiate jupyterlab. We first gotta activate the virtual environment we just created, and then we simply call the jupyterlab or jupyternotebook IDE inside that project folder or the course base folder, and we will have access to all these projects folder inside that same virtual environment that will be in turn already integrated to the jupyterlab IDE. So we simply call the jupyterlab and open the IDE with access to all the projects available or to be created through this IDE. Then for each of our projects and inside each respective folder for that project, we will create a notebook whose extension is .i, py, and b. Py is from Python and NB is from notebook, so .i Python notebook. And inside that IPython notebook, we're gonna write all our Python code, our source code, as well as some markup code. You see that notebooks actually are not pure Python scripts. They're a mixture of Python source scripts together with HTML or with markup code that translates to HTML. So we have both the source code, the Python code itself, but we can also use markup text, and you'll see that it's pretty nice for writing a script because you can describe some parts with markup or HTML code, and the script itself you put in the code cells separately, but visually it's much better than if you only wrote the code script itself. So we'll see all that when we create our first notebook. Then after we conclude our notebook, after we write all our code, we'll use Git to add those just written files to the Git staging area, which is the space area of Git that stores all the files or the state of files that are going to be committed. Then after we add, we'll commit, and this commits locally. This git command does not commit to the remote servers at GitHub, it only commits locally, but we gotta do it first locally for later pushing it to GitHub. So we first add the alterations we do, for example, to our IPython notebooks, then we commit locally, and finally we push those committed files or data to our GitHub remote corresponding project at GitHub. So we work always with Git locally, and after adding and committing, we push that to GitHub remotely. Then finally, when we finish our project and commit and push all the alterations for GitHub, we'll have both locally as remotely the same project with the same alterations or the same data, and then we can integrate the GitHub projects directly with Google Colab for running that GitHub project source code at Google Colab shared servers. So we must have an operating system and a server for running our Python source code. So at GitHub we only have the source code, but for running that, either we must clone it locally to our own machine and run it locally, or we can send that GitHub source code to any remote server, for example, the ones we have freely at Google Colab, in order that that server can take that source code and start it through its own Python virtual machine and all the remote environments that will be available for us from Google. So we'll integrate the GitHub for sharing our remote source code project with Google Colab, and Google will use that shared project source to run it at Google servers, and we'll see not only the source code, but the source code running at real time through the integration with Google Colab. And finally, you can share both the source code through your GitHub project link as the execution of that code through Google Colab link of that respective GitHub project accessed from Google Colab, and share that with anyone you like, and the one that receives the link can either open the GitHub link or the Colab link if the person wants to see that code running. And the person, of course, can clone that GitHub repository locally and recreate the virtual environment locally using Anaconda also, or use the Colab link to see it running remotely. So this is it. This is our basic workflow we're gonna use. Of course, we have much more advanced workflows that can be used, as I said, with continuous integration, continuous deployment, web services workflows, and all that. But this is the free way and most professional way I see that we can use during this course, and that I use all the time for my projects, so that we won't have to pay anything for Amazon Cloud or any other cloud for running these projects remotely. We can simply run them for free, either locally as at Google Colab. So one last thing that I wanted to share with you before we actually start coding is how Python, either from an IPython notebook or from a pure Python script, how Python takes that source code and executes in your machine processor. So this is a general architecture description of how we do that. For example, consider that we have concluded writing our IPython notebook or a Python file with a pure Python script. In the case of Jupyter notebooks, we have, as I said, some space where we have code cells with pure Python scripts. We have the markdown cells that we're also gonna use a lot, and that translates to HTML, not to Python. And we have the execution output, which is the output of the code cells that we run directly at the notebook. So we have basically these three spaces inside a notebook. We have the code cells, the markdown cells, and the output cells. So what is executed from this when we run a notebook code or source code? Basically the code cells with the Python script. When we run the notebook, what happens is that the code cells will have the source Python code extracted from the notebook and put into a python.py file, which is a basic Python source file that we could write directly or using the notebook code cells. And then what the Python virtual machine will do, actually it will do two things basically. One is to compile the code and the other is to translate that. And I'm gonna explain how that is done here in detail. So the first thing, when the Python virtual machine takes the source Python file or the .py file with the Python script or code script, is to compile that Python file into an abstract syntax tree. It's a data structure inside a syntactic data structure that Python uses for later then translate that to bytecode through the bytecode generation. So the Python compiler, for example the CPython, it takes the py source file and compiles that to an internal syntax data structure that the bytecode generator also inside the compiler translates to Python bytecode. So here at the bytecode, it's not .py language anymore, it's .py-C bytecode language. So it's a lower level language than Python itself that then is used by the bytecode interpreter and Python virtual machine, which takes each line or each unit, for example a function of a bytecode, not of Python source code but of bytecode, and it keeps looping for fetching, decoding, and executing each piece of code that it takes until it translates or executes all the bytecode from our source code. So one thing very important here is that Python source code, after being translated to Python bytecode, it actually is never translated to native code or machine code. Why? Because, for example, for CPython, which is one of the many available Python virtual machines composed of a compiler and of an interpreter. It's one of many. I'll show you the other ones in a moment, but CPython is the reference one. It's the official Python virtual machine, both the official Python compiler as the official Python interpreter. This interpreter of Python or this Python virtual machine, it never actually translates the Python code to machine code. What it actually does is to fetch and find at a CPython runtime code a correspondent function that executes that same code function from our bytecode. So it doesn't translate the bytecode to machine code. It fetches each line or each unit of code at our bytecode, and for that piece of code it looks for an equivalent function at the CPython runtime machine code, which is already a compiled high efficient compilation of the CPython runtime, and then it runs the CPython runtime function corresponding to that bytecode function, but it doesn't translate the bytecode to machine code. It uses the machine code already compiled at the CPython runtime code to execute that same sentence or that same calculation or process at the runtime code, which is already a machine code. It's not a machine code that comes from the bytecode. It's a precompiled machine code with all the possible functions that can be called at our processor, and with equivalent functions that relate to the bytecode functions of our code. So the PVM actually does not interpret the bytecode to machine code. What it actually does is to dispatch a correspondent function at the already compiled CPython runtime code, which is a machine code, but not compiled at runtime. It's a pre-compiled machine code with a lot of functions, and finds the correct function corresponding to that function at our bytecode. So it fetches, for example, one line of our bytecode, a function, for example. It looks at the CPython runtime precompiled native code, which function would do the same procedure of that bytecode function, and then it executes that correspondent function by sending it to the operating system, and the operating system to our processor. So remember always that CPython runtime is, in this case, a C language precompiled native code that has all possible functions to be called at our processor, and for each line or each unit of code or function at our bytecode, there will always be a corresponding CPython runtime precompiled code that can be called a machine code corresponding to that bytecode that is called through the operating system at our processor. So only then using the processor registers, the cache, and the arithmetic and logic unit of the processor itself. So what is processed here at our processor is never the code we write or the source code, neither the bytecode translated from the source code. What is executed at our machine processor is some of the functions of this precompiled CPython runtime native code. So our source code and bytecode are never translated to C or are never translated to machine code, but the Python virtual machine simply fetches and dispatches to a correspondent function or functions at CPython precompiled runtime machine code, and that machine code specifically is the one that the operating system sends to the processor to be executed and return some result. So here another architecture overview. We have the interfaces and inputs. For example, our Jupyter IDE that create a Jupyter notebook, IPython notebook file. The code cells of that notebook are compiled to an abstract syntax tree, which is the internal syntax data structure that Python uses at the Python compiler and at the Python bytecode generator. That syntax sequence or tree structure is translated to a bytecode, a Python bytecode by the bytecode generator after the compilation to the abstract syntax tree, so that AST is transformed to a Python bytecode. So we have the source code here at the notebook. It is compiled to an AST, abstract syntax tree, and that AST is compiled to a Python bytecode with a .pyc extension by the bytecode generator. That bytecode then goes to the interpreter or Python virtual machine, which, as we've seen, actually does not translate the bytecode into machine code. It simply dispatches the functions of the bytecode to the correspondent already precompiled functions at the CPython runtime machine code, and then the operating system uses that functions from the CPython runtime executable with the native code, sends that to the processor of our CPU, which then executes in a processor level and returns a result. So ultimately, every programming code is executed by our CPU, and it must be in a native format, not in a source code format or in a bytecode format, but in a native format corresponding to our CPU architecture. The code that's going to be executed must be already translated, for example, or created or precompiled in this case to the specific processor architecture type. We can't execute high-level code or bytecode in our processor. That's why we have this whole architecture from the high-level source code to the AST and Python bytecode, and later, after dispatch through the Python virtual machine, the execution of the precompiled native code corresponded to the functions of that bytecode. This CPython runtime native code is the one that's going to be executed at our CPU or processor. One recent thing that's been added to the Python architecture is one that already existed with Java and JavaScript and C# and other programming languages, which is the just-in-time compilation or JIT. For Python, in this case, it's been added in the case of CPython PVM implementation. It's been added recently, 2 years ago, at Python version 3.13. We are now at Python 3.14, so one version ago we had added to the CPython PVM implementation the JIT just-in-time compilation, in this case a partial JIT, but for other Python virtual machines we also have the complete compilation of the code. For example, for grow VM, we're going to see on the next slide at least the main types of Python virtual machines. We are showing you here the architecture for the CPython specifically, but we have some variation between the different implementations of Python virtual machines. This whole explanation here is for CPython specifically, but even for CPython it's been introduced a partial JIT experimental compiler. In what just-in-time compilation or JIT compilation does, it takes parts of the bytecode in this case and translates directly to native machine code. So it not only dispatches to equivalent functions at the CPython runtime. For most of the bytecode it actually continues to do that, but for some parts of the code that are repeated over and over again, also called hot codes or hot pieces of code of that bytecode, it actually takes those pieces of code and compiles at runtime to native code in order to call it faster. So you have not only the CPython runtime native code, but also the JIT compiled native code from the hot codes from our bytecodes. So we still have most of the native code being called from the CPython runtime precompiled native code and not from the bytecode, but now we may also have, through JIT compilation, some small pieces of native code directly compiled at runtime from some pieces of our bytecode as well. So it's very important, the just-in-time compilation for hard parts of our code that are executed many times, because it adds a lot of efficiency and velocity to the execution of our code, instead of simply dispatching every single function of the bytecode to a pre-existent CPython runtime native compilation. So finally here we have some major implementations of the Python virtual machine, starting from the reference one, which is the CPython, which is the one we've been talking about all this time, and which is the one we're going to use throughout this course. But I'd like you to also know that we have others. We have the PyPy, we have the Jython, we have the IronPython, and we have the Grow Python as well, and others also. In the case of CPython, we have the Python source that is compiled to an AST, as we saw. That AST is translated to a Python bytecode, .pyc, and that bytecode get into an interpreter loop, which simply dispatches. It does not translate, it simply dispatches the functions of the bytecode to correspondent functions at the precompiled runtime native code, which is the one that is executed at our CPU. So this line here is what we've just seen at the previous slides, but here you have the variations for the other implementations of Python virtual machines. For example, for PyPy, that has been using JIT compilation way before CPython started using. So the main difference between PyPy and CPython is that on the PyPy Python virtual machine, it has JIT compilation by default. And we have here some differences also at the compilation with RPython instead of a C compiler, as well as the bytecode is a little different. It's a PyPy bytecode instead of a Python bytecode .pyc bytecode. Here it's all related to C language at the CPython. That's why you have the C here at the initial of the Python virtual machine name. Here at the PyPy, otherwise you don't. So you also have the Jython Python virtual machine implementation, which actually uses Java for compiling the Python source code into that class, Java bytecode, and then, as in Java, that bytecode is run or interpreted at the JVM instead of in a PVM. It's executed at the JVM, and the JVM itself calls the native methods at the CPU. We also have the IronPython PVM implementation with .NET integration. Instead of a JVM, you have a .NET Common Language Runtime implementation that takes that compiled code and runs it in a native level using the .NET platform. And finally, we have the Grow VM virtual machine implementation, which uses a common parser for any language that Grow VM uses. It parses it into a Grow bytecode. Either it's Java or Python or any other programming language, and Grow bytecode then is run at Grow VM, also with JIT compilation. Here showing translated from Python source code or JavaScript or Java or Ruby or any other programming language, as I said. That's why it's meant to be a polyglot compiler and interpreter. And GrowVM, which is the native code compiled, executes that at the processor level. So I just mentioned these main Python virtual machine implementations so that if you're curious about the evolution of virtual machines and also with the integration of Python with other languages, for example with Java, .NET, JavaScript, and even polyglot integrations of many languages at your source code to be compiled and run by virtual machines, for example Grow VM machine, in a single code execution at your processor. Then you can print and paste this image to ChatGPT or any other generative AI prompt and ask it to explain you, and it will explain all the differences and when to use each one of these Python virtual machines. But for our case and for the whole course, the Python virtual machine we're gonna use is simply the CPython, which is the reference implementation or the official implementation of a Python compiler together with a Python interpreter with a C language implemented native code of this Python virtual machine. So, and the last thing that I wanted to show you before we actually start coding is the CPython official project at GitHub, which is github.com/python/cpython. You can check all CPython versions there. Also, the other implementations of PVMs. They all have their own GitHub projects. They are all open source projects. So for CPython, you have it here at this address or URL. And also the official site for downloading CPython is python.org/downloads, the official Python organization. But as we've already said, at least for this course, you should not download the sources for the CPython here from GitHub or download the complete package of CPython of any of these versions from the python.org, because as we said, we are gonna use anaconda to create our virtual environments, and for each virtual environment you create, you pass the dependencies that the environment is gonna use, and one of those dependencies will be the Python virtual machine. So you won't have to download it from anywhere, because conda will do that for us. So Python, the Python virtual machine, will be one of the dependencies that we're gonna download to our projects, but that will be done by conda automatically. Conda will manage all those dependencies for us, including the Python dependency itself. Okay, that's all for our workflow preparation. So now we are ready to start coding our first Python project. See you in a moment.